Hi, this is Sylvia, and welcome back. I wanted to hit a point on finding a solution in dealing when you're using a fiber section for a beam element in a 3D model and you're using rigid diaphragms. The problem with doing that is as you use the rigid diaphragm constraint, you're actually imposing some additional axial forces into your beam element, which when you have a fiber section and you have yielding in your element wants to elongate. And because you're constraining the deformations, you end up having these additional forces in your beam, which increase the strength of your beam. If that's what you want, fabulous, that works. But most of the time you don't. You just want to have a beam to be itself, and you can almost use a uniaxial section if you want, so that you don't have PM interaction. But sometimes it's just so much easier to find a fiber section. Yes, it's computationally more expensive, but I don't have to spend the time trying to figure out what the capacities are. So there is a way around it by just adding to your fiber section an additional axial strength behavior or an axial behavior where it's pretty much flexible in the axial direction. So you're adding a release in the axial direction, and therefore you lose this PM interaction in your beam. This is very easy to do in eSEES, and so I'm going to show you that. And it's not just easy to do it, but it's just a good way to evaluate this model. I'm not 100% sure that this is the right answer, and so I'm interested to find out, what are the effects. So what I've done is in eSEES, I've built two different models, and of those two models, then I have two different cases. I have one model where I have fiber sections for beams and columns, but in one model, I retain the PM interaction in the beam element. In the other one, I release it. So there is no PM interaction, which I think is what you should do when you have a rigid diaphragm constraint. And then I do a pushover analysis and an earthquake analysis with these two models. And for each case, I do a rigid diaphragm constraint and then just a flexible diaphragm constraint, which means really just no diaphragm at all. And let's look at what the results are and how we go through this. So I'm going to walk you through what I did with eSEES. I started just a project, a new file with everything new. And what I'm going to do is I'm going to define a very simple reinforced concrete section. So first I define my concrete. I'm going to call it a confined concrete just so that it has some sort of ductility, but not too much, and no tensile strength. So this is very sensitive to PM interaction. So now I'm going to define this section, which is just going to be a square section with this concrete, and P releases off. So that means it's just a regular fiber section with PM interaction. I can save it. I'm going to give it a special name, test it. This is what it looks like under zero axial load. Then I just turn on the P release, test it, does the same thing because you're not going to see that here. It's how it goes into an element that makes a difference. So I've saved it under a new section. I can test it under different axial loads, and you will see that it's sensitive to the axial load, and the behavior is the same in this case for the two sections. As I said, it really matters when you put it into your element. So once I'm done with testing this section and the different material, I'm going to build a simple elevation. This elevation is going to have, my columns are going to have PM interaction. So it's going to be the rigid axial model, which is what I've called it, okay? And so at both ends of the element, I've got this. And then for the beam, I'm going to just define, for this first case, I have PM interaction. I'm going to give some gravity loads, just basic ones that are not too high, not too low. And I'm going to save this model. Then what I'm going to do is I'm going to remove the beam and replace it with one that has, the free axial. So this has got the uncoupled. So only for the beam, right? Because you only care about the beam element having no PM interaction. So there it is, and I just save it under a new name, and so all the gravity loads and everything is saved. Now what I'm going to do is I'm going to build a new elevation that's just the beam, because I'm going to put these into a 3D portal frame. So I really just need, for the out of plane direction in the Z direction, I really just need to add a beam. So just to make things simple, I'm going to have one beam, which is using the PM interaction, and then the other beam is going to have no PM interaction. And so that's how I've defined my different elevations. What I'm now going to do, there's the beam, and I'm going to save it under a new name. There it is. And saved it. So now I'm going to go in and build my 3D model. First, I have to build a grid, which defines the length of the bays. This is just going to be a simple bay. I don't care about the length, so I'm just going to take the default grid to start with. So now for the 3D model, I'm going to use that grid, and then carefully I'm going to place first these elevations in the two directions, and then just the beam in the other direction. And there it is. I've got one model, and I'm going to save it. This is the one with PM interaction. So I'm going to save it as is, and then I'm going to turn on the switch for rigid diaphragms, do it for all the floors, and then I'm just going to give it a new name, and it's saved. So now I already have two 3D models that I've built. I'm going to go through the same process now for the other one where I have no PM interaction, so it's free axial. Remember, that's just for the beam. So there I am. I've put in those elevations, and then I put these beams. Now I've got my third frame, which has the flexible diaphragm. I'm going to save it, and now I'm going to save it again with rigid diaphragms. Now I've got my models. I've defined my models. I've defined the gravity load. What I now need to do is define the lateral load. It's always important to save it, and there's some glitch in here that I want you right now to save it and maybe even rerun the saved file. Okay? So now what I'm going to do is define my earthquake loading. I'm going to subject this to earthquake. So I define a load for earthquake, and then I'm going to put that into different load combinations. So in this case, I've got gravity only. Then to gravity, I'm going to add a pushover analysis, and I'm going to make it go to a maximum of 10 units. Right now I'm working in inches, or maybe just 5. So that's my pushover analysis. Now I remove the pushover load, and I put in my earthquake, and I'm going to save it under earthquake. So now I've got 3 load combinations: gravity, static pushover, and the earthquake. I'm going to save it, and I'm just going to rerun that file. It just reloads it. And here is the input file that I have in eSEES. As you know, this saves it to a script, and if you want, you can work directly within the script. Other than, the default elements and materials, there's also here you could see the 2 different elevations. If I make it bigger, you see that the difference is literally only in the columns are the same, but the beams are different. So there's you could go see the difference between the rigid axial, and then there's my flexible axial for the beam. And then these are the 3D model, the 4 3D models. So now I'm ready to run the analyses. The very first thing you should always do is check gravity and your mode shapes. So I'm going to display the mode shapes and look at the periods. I'm going to do it for all 4 of them. You find out, look, it's 4.22 and 0.152, and it's actually going to be the same period for all 4 cases, because there really isn't any difference in the geometry. It's just really releasing the PM interaction. What I now want to do for all of them is to run a pushover analysis. If you want, you can even look at the pushover analysis for just the 2D elevations as well, because that's what's cool about it. It's actually, they're always the first step. You always want to test your 2D frame. And that's what I'm doing here. And you can see that first one actually had a little glitch, and so does this one here in the lateral load capacity. Now I'm going to run lateral load in the other direct for the 3D frames. And I'm going to speed this up. Actually, I'm going to let it run. It's not that slow. If you want, you can always just scale these higher. I'm going to run these right now live and watch them run, and then I'm going to look at the results of the analyses. I also have in one direction and then in the other direction. That's why you see it's because it's a 3D frame, but I'm only loading in one direction. In the Z, you just see pretty much noise. What I'm going to do is I'm going to collect the pushover response curve for all the different cases. I'm going to put those into Excel, but maybe first I'll just open up the windows for all 4 cases, just for pushover. So you press a little plus, and that puts it into its own little window. I set it aside, and I'm going to do this for all 4. so I can compare the results. Now, very, very important, this is a displacement control analysis where I have the same masses at all the same nodes. So I am not going to get any difference between a rigid diaphragm constraint and a flexible diaphragm constraint, because I am forcing the displacement to be the same because I'm applying the same forces. But as you can see, there is a significant difference between the model on the left, which is the one that I have PM interaction in the beams, and the one on the right that doesn't have PM interaction in the beams. And so what happens, that PM interaction, as the beam yields, it increases the strength of your beam, and therefore it increases the strength of your overall system as well. And so you have to be really careful when you have PM interaction in your elements. What I'm going to do now is I'm going to show you the moment rotation or moment curvature results for each one of these cases. And you'll see that, the moment capacity when you have PM interaction goes up. And also remember, because we're pushing over and because of overturning, the axial force is increasing in this beam as well. And I will show you the plot there because we're going to want to look at the axial force. But so now if we compare these two strengths, so first I'm plotting the capacity, the moment curvature response of, the one with PM interaction and the one without PM interaction. Significant difference. And so if I now go back to my sections and I test those, so let's say I just do a basic pushover on that, under zero axial load, let's see, I should get the similar results as what I got before in my overall model. So I go in and I play with the numbers here a little bit on the pushover, so I define what points I want it to go to, because there's just not enough data points in this analysis here. And so now I look at this curve. This is for zero axial force. It doesn't matter which element I'm looking at or which cross-section I'm looking at. So I'm going to copy these data, put them into Excel, and plot these. And look at this. It's exactly the same curve. I'm going to put it in there. And you see it's exactly the same curve as I had for my beam for the case of an uncoupled section, which makes sense because the beam in that section is under zero axial load. And so it has a capacity of zero axial load. Now what I want to do is I want to look at, okay, let's look at the case where I have PM interaction. What were the axial forces in my beam? You see the increase because of the overturning. But I can see here that I'm going to maybe an axial load of over 30. So now let's go to my cross section and plug in the value of an axial force of 30 kips in, it was negative, so we're going to put it in negative value of about 30. You need to scale that a little bit, so let's go to about 30. It doesn't matter because it was increasing. I test it. So remember, this is the moment, I'm going to get the moment curvature response of this fiber section under a constant axial load. So it's not quite representative of what I have in the beam, but it should give me a similar moment capacity as to what I cross in my analysis. So if I take this data and paste it here, there it is. You see, the capacity does cross with what the demands were in my beam. And so that tells you that, yes, I'm getting consistent results where I have PM interaction. Now let's do some earthquake analyses of these. And what I'm going to do is I'm going to divide them all between the 4 screens so you see them at the same time. So now you're going to see all 4 models. They're labeled here. What you're going to find out are the ones on the right that have the flexible axial response are going to just die out real quick. It's just the concrete can't handle that. While the ones on the left with the rigid axial, so they have PM interaction, they can actually go a little bit further. Again, it's an unconfined, simple concrete section, so it doesn't make it through the whole time history, but you really see the difference in the effect of PM interaction in your beam. So now I'm going to go in and collect similar data as I had done before. Now what we're going to find out is whether you have a rigid diaphragm or not, you get the same results. And that's because we have a symmetric section, the masses are evenly distributed, so there is no eccentricities. And so I don't really see a rigid diaphragm really needing to make a difference. But it's just here to kind of, to make sure that I have all 4 cases. If we had some more 2D effects, then I would see a lot more. But we do find out that the difference in response, whether you include PM interaction or not in your beam element, as you can see in the comparison right here, is significant, big time, and is as expected. As you increase the axial loads in your beam section, you're going to increase its capacity. And so if I take the data and I plot it, even though we already have the response here, those two are of course the same, just to prove it to you here. It's always good to check. Make sure that if you get the results that you expect, then that means your model is what you think the model is about. So if I put the 2 sets of figures on top of each other, which is kind of what I'm going to do right now here. So there is no effect as expected of having rigid diaphragms in neither one of the 2 cases. If I, on the other hand, compare the case where I have PM interaction in the beam versus no PM interaction in the beam, what do I see? Well, you see it, and it's kind of hard to see it, that's where it ends, right there. The other, the element that has more capacity in the beam definitely has a longer resistance to the earthquake. So we can almost say it collapses later. And here's a figure right here that shows you the significant difference between them. If I now go and look at the beam response, and I look at the 2 cases for the moment curvature response of each one of the 2 beams, I'm going to grab this data and I'm going to put it into Excel. So I'm going to start a new observation here. So I'm going to plot these. Of course, there was some bad data, so I'm just going to kind of change the axes to the region that I'm interested in. So there it is. This is the behavior for, it's nicely labeled when you copy the data. And so if I go in and grab it for the other model as well, and I overlap it, ooh, you can really see that something interesting is going to come out of this. So if I paste these into Excel and I plot it, and then I overlay one on top of the other, and I got to deal with the axes, of course. Should have pasted one plot on the other one instead of this way. You could see the significant difference in moment curvature response between the 2 models. One is increasing in axial load and the other one isn't. If I now just look at the concrete strains just for kind of fun in the section, that is for one case. Now I'm going to go in and look at the PM interaction beam and grab the strains. This is just in some random fiber, it doesn't matter, just to kind of show you that you can look at, even that makes a difference when you're looking at stress strain in the concrete. It just never quite goes into enough compression for the concrete. You see it there, that the concrete doesn't go into enough compression, it stays a lot in tension, and then it really limits the forces that it can resist, because remember, you've got concrete on both sides of your section. So this is a really good evidence here of just showing the response of where it finds in the 2 cases. This is if I look at the strain response over time. Just doesn't really tell me much other than, hey, I don't even manage to make such large strain deformations. Now look at the actual OpenSees input files. On the left, I have the one with the beam with a PM interaction, and on the right, I have the one with the released axial, so no PM interaction. You could see that the initial input is pretty much the same. They both have rigid diaphragm input, but for the second one, what you need to do is I need to define 2 different sections for the columns and the beams, but also you have an additional component to your fiber section, which is the P release, the additional infinitely flexible section in your section aggregator. And I'm going to get to it right there. So that's the material that has a very low flexibility number. It's not 0, it's just a significantly small number. And if you scroll down, you will see that I get to there. And there's where I define the section aggregator for the beam, where I have material 11 for axial force. And you don't see that on the left-hand side nor in the column. And so this is just a tiny little trick that I learned to remove PM interaction from an element without putting in an additional zero length element with no stiffness. So it's all done within the fiber section. If you now go in and scroll the two files, you look at the rest of everything. Recorders and analysis and loads are all pretty much the same for the two cases. So the only real difference is having to define that additional section, but you would for beams and columns anyways, and then just the fact that you've got that axial release. If you look at the input file for eSEES, which is a little bit simpler, there's my two sections. One has the PM axial release and the other one doesn't. And then those are placed into your elevations. There it is, right there. I have rigid axial and flexible axial for the beam. And then when you define your 3D frames, of course, they all correspond to the proper elevations. So I hope this was helpful. I think it's a nice little trick. You can do it directly in OpenSees, but of course eSEES makes it easier to generate many files and do your study. Well, thank you for your attention, and have fun with OpenSees. Bye-bye.